Okay, so we're given certain information here. We're given this is 18 centimeters. We're given our radius is 3.17 centimeters. CG is a diameter. AG here is 120 degree arc, which of course means that says something for this angle. Now, is that angle going to be 120 degrees? No, why not? It's not at the center. Right? If it was at the center, it would have to be 120. The central angle would have to match the arc. We also know that it's a right angle because we gave that right angle there. But anyway, that has to be a right angle. So that tells us also that it can't be at the center. But we do know that this angle here has to be equal to the average of this arc and this arc. Because it's formed, both of those arcs are formed by those two lines. Remember that rule? That these angles have to be the average of those two arcs? So 120 plus x, if I call it the arc CB there x, 120 plus x over 2 has to equal 90. Does that make sense? So I'm going to multiply by 2. 120 plus x equals 180. Subtract the 120, x has to be 60 degrees. So what that's telling me here is arc CB is 60 degrees. I was asked for arc BE. Arcs are additive and subtractive. So if I knew arc CE, I could just subtract 60 from it to get BE, correct? Well, if I knew this angle here, I would know arc BE because that's a central angle, correct? Well, that angle is 160 degrees. How do I know that? What's this angle here have to be? That's a radius to a tangent. Has to be right angle, correct? What's this angle here have to be? The fact that I just drew a square box in there probably means it's a right angle, right? So 90 and 90 is 180 plus 20 is 200. This is a four-sided figure here. A four-sided figure has to have an angle sum of 360. So I've got 90, 90, and 20. This has to be 160 to add up to 360. Also, by the way, there's a little rule of if you have two tangents like this, the central angle here is going to be the supplement of this angle. But just because these two are both 90, that's 180 added to 360. The other two have to be 180. So that's 160. That means that whole arc is 160, which means this portion of the arc here is 100 degrees. Just the 160 minus 60. Any questions on that? Angle CFE I just found. That was the 160 degrees. That's right there. ED.
Your BE was 18 for the arc.
That's the arc. Yeah, that's the arc right here. I wasn't asking for the length of the arc, just the degrees of the arc. ED has to be 18 centimeters. You got it, because it has to be the same as this other one. Two intersecting tangents are the same length. Yeah, if you would have put down a length for that, if you'd have taken the, the circumference of the circle times that, whatever, the 100 over 360 to get the actual length of it in centimeters, that would have been fine too.
I thought that too, but isn't D to G the 18?
D to C.
Yeah, that's 18, but isn't that the same as D to G on the bottom, not D to E?
No, D to E, the tangent stops at E.
DG be the same.
DG would not be the same because it wouldn't be tangent there. It couldn't be tangent there because CG is a diameter. If it was, you had a tangent at C and a tangent at G, they'd have to be parallel to each other.
Well, we're talking about a regular shaped cone, right?
Yep.
So the length would be the same from any point on the circle.
Nope. If you pick a point out here and you draw it up to its point of tangency, will be the same length. But it can only be tangent in 2 points. There's only 2 points that will be tangent to a line through this point. C and E are the only lines that can be tangent. They're the only spots where you can draw a tangent line from D. If you drew the line to G, it wouldn't be tangent. It'd actually cut through the circle a little bit here. So you think of it like this. If I pick a point here, right, I can draw it. It'll be tangent there, and it'll be tangent. If I drew it right, it'll be tangent here. Any other point, it's going to have to cut through the circle to get to it, so it can't be tangent there.
So it's not a regular shaped cone.
Oh, it is a regular shaped cone, but a regular shaped cone is not really a true half sphere on top. A regular shaped cone is always slightly more than a half sphere on top. When we did our problems last semester, we assumed that it was a perfect half sphere on top, which is actually not a regular cone. A regular cone, the top is actually more than half of a sphere. Because if you had a circle and you draw in a diameter, if I draw a tangent to this end of the diameter, it forms a right angle. Tangent to this end of the diameter forms a right angle. These two lines have to be parallel. They can never intersect. So when we're doing volumes, we do a theoretical cone with a half sphere on top, which is not a true full filled out cone.
It's not making sense. If you had a cone, and any distance around there to the point would be the same.
Well, you're just talking about a cone like this, though. The circle's laying flat.
Right.
This circle's not laying flat. The circle is in the same plane as the lines. And a cone, and a true cone, that circle you're thinking about, the end circle, is perpendicular to the plane that contains the lines.
That's why I wasn't.
Oh, sure. Yeah, these are in the same plane, so that this is not the end of the... This circle's not the end of the cone. It's a circle inside of the cone. So anyway, HF. Anybody find HF, this distance right here? Anybody know what AH would be? Same from 8 as H to B, yeah. That would be 3, half of the 6. We know this is 3.17, right? So, minus 3 squared. Because the 3.17 is the hypotenuse. .024. There it is. Questions?
At 1.0489. I'm wrong. I don't know.
You might have, no, because this number, 3.17, is actually rounded off. If you use 3.17, that's what you got to come up with, is 1.024. Any questions on those? Okay, so next thing I want to discuss is just some basic geometric constructions. And what I mean by that is just some things that you can do to copy shapes or whatever. Now, what I'm actually talking about is, I don't know if I even have it up here anymore. Yeah, I do. You guys ever seen these things, the protractor? Obviously, yours is probably a little smaller than this. But you have the point where you plant the point and then you trace out a circle or whatever. Well, these things can be used for a lot of stuff. That's my little adaptation, so it can be used on the whiteboard. Duct tape's good for everything. So anyway,
Interstate and duct tape.
it is actually blue, but is it painter's tape? No, this is blue duct tape. So anyway, let's say I have a segment and I want to copy its length. Well, I can just take a straight edge or a ruler and make a segment that I know is at least as long as the one I want. Then I take that compass and I put the point on one end and I extend it out so that the pencil, the tip of the pencil, is at the other end, and I can lock it into place. And then I use that then to just come out here and mark out the length. So you can use that compass to mark out lengths. If you have a good compass that's locking, and by locking I mean you get the one with the little screw in the middle so it cannot move at all. They use that for scribing and stuff like that, to use a uniform length away from a surface for countertops and things like that, and cabinets. A little bit trickier. Let's say I have an angle I want to copy. Well, I'm going to start out by just drawing a line with my straight edge again. Then I'm going to take that compass and set it to a length, and I'm going to draw an arc here. Then I'm going to come over here and put the end of the compass here and draw the same arc here, making sure it's big enough that it'll cover the width of the angle. Then I bring my compass back here, and I set the tip on one side and the tip of the pencil where that arc strikes the other side. Then just over here, strike that arc, use my straight edge to draw it in, and I've copied the angle. The angle should be identical. Obviously those aren't because I suck at drawing. Get the picture? The compass can be used for making right angles, for making parallels, all sorts of things. The only other one I'll show you here is, let's say I have a line and I have a point here and I want to draw a line perpendicular to this line through that point. Well, all I'm going to do is take that point, and I'm going to take my compass, and I'm going to set a length with that compass, set a width of the compass here, and I'm going to just strike an arc like that. So what I've done here is these 2 points that I've created are now going to be equidistant on either side of wherever that perpendicular is going to be. So I just flip my compass. I take the point and I put the point here and the pencil out here, and I mark an arc there. Then I move the point here and mark an arc there. And the line that connects my original point to that intersection will be perpendicular, that original line. So there's actually a lot of little simple things you can do if you all of this. The only reason I'm bringing this up is all of this is possible because of the rules of circles. Because if this were a full circle here, this is going to be a radius of that circle. This is a chord of that circle here. And the radius is perpendicular to the chord if it cuts the chord in half. So all we were doing there is taking that chord, that length, we artificially made that length by picking a radius with our compass. And then we cut that chord in half, and when we cut it in half, that has to be perpendicular. All of these constructions we are doing come off of rules of circles. Just like this one here. If this were a full circle, the length of the arc cut by this angle has to be the length. If that's the same as the length of the arc cut over here, then the central angles have to be the same. As long as those circles are the same size. So it's all off those rules of circles. I'm not going to get into a lot of details on constructions because we don't do them anymore. You guys have Mastercam or AutoCAD or whatever you're going to use that does those constructions. You just click on the point, click on the line, and pick a tool that says draw perpendicular, and it'll do it. But this is really the thought process that computer is going through, is these constructions. It all comes from the rules of circles. Well, the good news, the very, very good news is we're done with circles. Very, very bad news is for over your weekend, I'll let you take this quiz home to finish it over the weekend, but also over your weekend, I'm going to send home Unit 3 test with you.
We're going to have a quiz and a test to do?
Well, the quiz